Today we are standing at a crossroad where thermodynamic reality meets the environmental necessity. So decarbonization in blast furnace iron making is no longer a peripheral research project. It's a now fundamental shift in how we manage the crucible chemical and thermal workload. By the end of this session, you will walk away with the three primary deliverables. First is a deep dive analysis into how pure hydrogen injection restructure the tier level kinetics. Second is a quantified understanding of 1 to 2 uh, return on investment where 1 kilogram of hydrogen saves 2 kilogram of carbon in coke. And the third, the ability to predict the resulting system while equilibrium in top gas temperature and blast air requirements. So look at the screen. On the left, we see the past, a carbon intensive process characterized by heavy particulate and high pollutant load. On the right, the future is clean energy, how represented by a blue arrow of hydrogen injection. This transition is about replacing fossil carbon with a carbon free reductant to achieve near zero emission. To understand how we get there, we must first address the industrial imperative to eliminate carbon at the very source of the process. As of 2019, hydrogen was virtually absent in industrial blast furnace, but today's carbon taxes have changed the math. Follow the flow on the graphic from the orange CH4 injection box on the left, which represent our current thermal load of 1500 degrees centigrade, sustained by a natural gas towards the bright blue hydrogen injection center. Notice how the final white box shows a 0 for carbon input. The so what factor here is simple. By replacing CH4 with hydrogen, we eliminate the fossil carbon at the start of the chain while still sustaining the thermal energy required for molten iron production. This is the ultimate hedge against rising carbon cost. We are not just changing a fuel, we are purging the carbon footprint from the thermal core of the furnace. It's a clean energy flow that allows us to maintain our 1500 degrees centigrade target without a baggage of CO2 generation. This transition requires us to mentally map the entire furnace ecosystem into two distinct continuous segments. So the two the two continuous segments are as. To model this accurately, we view the furnace as a two reacting segment divided by a dashed line you see on the diagram. The top segment receives the solid charge of iron oxide and coke at 25-35 degrees centigrade ambient condition, releasing the top gas exhaust consisting of CO, CO2, hydrogen and water vapor. Below the line is the bottom segment where the real magic happens. Notice the blue arrow for hydrogen injection and the white arrow for the blast air at 1200 degrees centigrade. The operational impact of this split is that we can now isolate the two-year zone kinetic. We are targeting a final product of molten iron at 1500 degrees centigrade with a 4.5 mass percent carbon content. By segmenting the furnace this way, we can precisely calculate how the injected hydrogen interact with the descending burden before it ever reaches the hearth, allowing for the tighter control over the final hot metal chemistry. This segmentation allows us to define four systematic shifts that completely redefine our diagnostic mathematical matrix. Coming to our four systematic shifts. So redefine the mathematical matrix. In process of that, looking at the diagnostic matrix on your screen, this table is the heart of our new modeling approach. Row 1 set our injectant specification to an extent continuous flow of 20 kg of hydrogen per 1000 kilogram of Fe produced. Row 2 shows the mass balance shift from 25% hydrogen in natural gas to 100% pure hydrogen. Row 3 is the clean shift that hydrogen introduces absolute zero carbon into the bottom segment. And finally, row 4 adjusts the enthalpy balance to account for hydrogen entering at 25 degrees centigrade with an enthalpy of 0. The so what here is that these four shifts simplify our matrix while simultaneously increasing the chemical demand on hydrogen as the primary reducing agent. We are removing the complexity of carbon-based coupled reaction and focusing on the direct kinetic of hydrogen reduction, which fundamentally alter the furnace's internal gas composition and pressure profile. With these matrix shifts defined, we can now visualize the intense activity occurring within the tuer injection zone. So now coming to the bottom segment dynamics, the tuer injection zone. Here you observe the mini map on the top right. We are now zoomed into the very bottom of the furnace. Here 20 kilogram of cold hydrogen collide with 1200 degrees centigrade blast air. The visual shows the orange tube of the iron oxide, specifically the FeO point, that is FeO, descending into a chaotic zone of blue and white arrow. This is where the hydrogen acts as a powerful reducing agent, stripping oxygen away from the iron oxide. The operational impact is the massive shift in the chemical and thermal workload. We are moving the heavy lifting of production away from the carbon heavy coke and onto the hydrogen gas. This reduces the burden on the raceway and changes the way heat is distributed in the lower furnace. By utilizing hydrogen here, we are effectively pre-reducing the burden in the most thermally intense zone, which drastically improves the overall efficiency of the hearth. This chemical shift at the tuer leads us to the most impressive economic benefit, the 1 to 2 ROI on the carbon saving. This graphic is what you show your CFO. On the left, a scale shows a 1 kilogram of injected hydrogen perfectly balancing 2 kilogram of saved carbon in coke. Now look at the linear graph on the right. As the mass of the tuer injected hydrogen increases from 0 to 25 kg along the x-axis, the furnace coke requirement on the y-axis plummets from 390 to nearly 340 kg. This 1 is to 2 ROI exists because hydrogen is more efficient reductant than carbon in these specific kinetics. The so what factor is dramatic reduction in your total fuel rate and a lower reliance on expensive metallurgical coke. You are buying a cheaper, cleaner gas to displace a more expensive, dirtier solid. Every kilogram of hydrogen you pump through these 2 years is 2 kilogram of coke you don't have to buy, transport or burn. As the coke requirement drops, we see a commensurate and massive reduction in the required blast air. So when you burn less carbon, you need less oxygen. It's a simple but profound stoichiometric reality. The radial graph shows two lines diving towards the bottom right. The blue line represents nitrogen in the blast air dropping from 983 kg to 948 kg. The orange line shows the oxygen plummeting from 298 to 287, 298 to 287 kg. So because the atmospheric nitrogen is reduced by a factor of 3.34 every unit of oxygen we save, the total gas volume force through the system drops significantly. The operational impact here is the reduction in the pressure drop across the burden. Lower gas velocity means less fluidization of the charge and a lower risk of flooding or hanging. This allows you to either increase your production rate or use a finer, cheaper burden while maintaining same aerodynamic stability in the furnace stack. These changes in the bottom segment feed directly into the top segment, ascending exhaust flow. The mathematical solution from the bottom segment now flows upward. Follow the arrow rising from the orange cubes of Fe2O3. We now have a newly altered ratio of ascending gases CO, CO2, hydrogen and a significantly higher concentration of H2O vapor. The matrix here must account for these gases interacting with a 25 degrees centigrade solid charge. The so what factor is the change in the thermal reserve zone because hydrogen reduction is endothermic compared to some carbon reaction. The gas to solid heat exchange profile shift. You will notice the large S2 arrow. This is the byproduct of our success. We have replaced CO2 with water vapor. However, this shift changes the gas density and the heat capacity of the ascending flow, which means your top gas cleaning system and moisture knockout pots need to be ready for a much higher aqueous load. This shift in gas composition leads to one of our most critical monitoring parameter, that is rising top gas temperature. Coming to this issue of top gas rise, this is a critical operational warning. So as we increase hydrogen injection towards 20 kilogram, the top gas temperature climbs steady, hitting 227. Unlike almost every other injected, hydrogen pushes this temperature higher. The so what factor is that this require active operational balancing. If your top gas gets too hot, you risk damaging the furnace top equipment or the filter bags in your dust catcher. To counteract this, we typically use simultaneous oxygen injection to manage the raft and keep the thermal profile in check. You cannot simplify or simply set and forget your hydrogen flow. You must balance it with your blast parameters to ensure that the heat is staying in the furnace is used for melting iron, not just heating the exhaust gas. When we manage this temperature correctly, we achieve the ultimate goal, that is slashing our stack emission. The ultimate goal of slashing carbon stack emission is the highlight of this upcoming slide. So as you can see, this now the maths comes full circle. So look at the decline in the mass of carbon emitted in CO and CO2. At zero hydrogen, we are at 345 kilogram. By the time we reach 20 kilogram of hydrogen injection, we have shaved off 30 kilogram of atmospheric carbon. The 2 kilogram of coke saved per kilogram of hydrogen translate directly into an equivalent reduction of stack emission. The operational impact is clear. You are meeting your environmental target while maintaining productivity. For a standard furnace, this represents a nearly 10% reduction in the carbon footprint of the iron making stage alone. So this is not just a greenwashing, it's a verified stoichiometric reduction in the amount of carbon being vented into the atmosphere, quantified by the diagnostic matrix we have just explored. So these individual shifts culminate in a system-wide state of new equilibrium. So this is your dashboard for the future of iron making. We have logged in our 20 kilogram hydrogen injection, creating what we call system-wide new equilibrium. On the left, we see the downward ripples. Coke requirements, oxygen blast volume and nitrogen blast volume are all crashing. In the center, we see the upward ripple. Our top gas temperature is elevated by 227 degrees centigrade. The core output is a massive total avoidance of carbon stack emission. The so what here is the realization that you cannot change one variable in a blast furnace without affecting everything else. This equilibrium map proves that hydrogen injection is a holistic tool. It is not just about emission, it's about a leaner, faster, and more gas efficient furnace that operates with a completely different internal chemistry than the furnace of last century. However, for this to be truly sustainable, we must look beyond the furnace wall to the source of the hydrogen itself. And that is all about our matrix, which proves that massive decarbonization is a physical and mathematical reality. The math works, but as engineers, we know that to truly eliminate atmospheric carbon, the hydrogen injected itself must be green. It must be produced via clean electrolysis powered by wind, solar, or nuclear energy. The so what factor for the industry is that the blast furnace is ready, our blueprints are complete, and our models are validated. The burden now shifts to the energy grid and the supply chain. If we can provide the green hydrogen, the blast furnace, the very heart of our industry, is capable of producing the clean steel the world demand. The matrix is ready. The grid you must follow to get the success